Hello guys, welcome to Eduxcite classes. My name is Monit and in today's session we will start with the torque and the moment of inertia. I hope you have watched my previous video. If not, just click on the YouTube icon. You will get the links and even the link is given in the description below. Okay, so please share this video as much as you can with your friends and your classmates so that it reaches to the masses. And if you want to have any one-to-one session or a doubt session, you can even chat with me. The link is given in the description, or you can click on the WhatsApp. The PDF of this video is available on my website. The link is given there. You can check the worksheet as well as the marking scheme is available. Okay, so there are certain formulas which are given in your data booklet that you should be aware of. The first one is the torque, that is nothing but the force times distance times sine of theta, where theta is the angle between the force and you can say the r, or you can say the force which is perpendicular with the distance from the pivot. Okay, whereas moment of inertia is the summation of the mass distribution into r square. This is the moment of inertia. If we have more than one object, we can find out the total moment of inertia using this formula if we know. And another way of finding out the torque is equals to moment of inertia times angular acceleration, that is I times alpha. Okay, so you should know how to use this formula. Now the torque tau is denoted by the force F about the axis to be the product of the force times the perpendicular distance between the line of action of the force and the axis of rotation. So it is simply written as force times distance if the force is perpendicular with the distance from the point of axis of rotation. In principle, the moment of inertia of any real extended mass can be determined by the addition of individual moments of inertia of its point masses. So we will do one question based on this also, so we'll get an idea how to use this particular formula. Okay, so I will give you certain time to pause the video. You can solve the worksheet in this particular video while watching it. I will give you time to pause the video and solve, and then you can check with the answer. Okay, so let us start. So make it happen and solve the question number 1. Pause the video and solve. Okay, so if you look at the A part, first of all we should know that how the forces are acting in this particular situation. So if I want to draw, let us say the first force, what I can say by looking here is that the weight of the rod will be acting vertically in the downward direction, right? Because this is the rod which is lying, sorry, this is the cable, so the rod will be like this. The weight of the rod will be lying over this and the tension in the rod will be in this direction. Okay, now we know that this is attached with the wall, so there will be a force, and this force will be, if you will see, it is balanced, right? So there will be one tension component here, one tension component here. So in order to counterbalance this, there should be one force here, and to counterbalance the weight and this, there will be one force here. So the resultant force acting at the point where the wall is touching the rod will be somewhat in this direction. We don't know the angle, so we just draw a force F in this particular direction. Okay, now once we have identified the forces and we know that it is being suspended horizontally and it is in a equilibrium condition. So what we can do is, whenever an object is in equilibrium condition, we have two conditions. One is the translational equilibrium where the forces are balanced, and one is the rotational equilibrium where the moments or the torques are balanced. Okay, so let us make an equation for translational equilibrium. So for translational equilibrium, what I can say that this will be T y and this will be T x. Similarly, this will be F y and this will be F x. So I can write down one simple equation like the horizontal balance. So T x is equals to F x. Similarly, and vertical Fy plus Ty is equals to W. So I can make these two equations using the translational equilibrium. If it is not clear, you can just let me know. Another way is using for rotational equilibrium. Now for rotational equilibrium, what I can say is that the rod is balanced. So you can take any point as the pivot point such that majority of your forces become zero, so that you don't have to consider their moments. Okay, so I can consider the moment because I don't know the force F. What I can do is I can consider this as the point of pivot around which the rod will rotate. Now if I want to find out the moments, you can see the forces which I need is, one is the weight and one will be my tension Ty, right, because this will be anti-clockwise and this will be clockwise. Now this force will not act because the reason being this is the pivot point, right, and the forces acting in the direction directly towards the pivot. So these forces, the horizontal forces, will not play any role in the rotational part. It has to be at a certain angle or perpendicular to the direction of the line of action of the rotation, right. So I can say Ty, so anti-clockwise movement or the torque will be equals to clockwise torque. So anti-clockwise one is Ty, okay, Ty will be into this distance is how much, 2, right, yeah, so this will be 2, Ty times 2 will be equals to W times 1. Now putting up the values, Ty, so Ty will be W by 2, right, so W is 58 by 2 will be 29 Newton. Also if you look, if this is angle theta, so I can say Ty is nothing but T sine theta, right. So if I want to find out theta we can use using the, this is 3, this is 2, so tan theta will be, so you can say tan theta is 3 by 2, so theta will be tan inverse of 3 by 2. If you do tan inverse of 3 by 2, I have a calci with me, tan inverse 3 by 2, you will get 56.3 degree, right. So theta will be 56.3 degree. So I can say Ty is equals to T sine theta. So T will be Ty by sine of theta. Ty we have already calculated 29, sine of 56.3. So if you solve for this, let me do it, 29 divided by sine of 56.3, you will get 34.85. so I can say 34.85769, or rounding off into the two significant figure, it would be 35 Newton. So this will be the answer for the A part, right. Similarly, now if you look at the B part, the magnitude and the direction of the force exerted by the wall on the, so we have to find out the force F and the angle theta as well. So what we can do is, for that we should know the Fx and the Fy. Now Fx is equals to, you can see this Fx, this is Fx is equals to Tx, and Fy is equals to W minus, so Fy, so for B we can say Fy is W minus Ty. So W is 58 minus Ty was 29, so this will also come 29 Newton. So we got Fy. Now for Fx we can say Fx will be equals to Tx, and Tx will be T cos theta, right. So fx is equals to tx and tx is equals to t of cos of theta. T we already calculated, so fx will be 34.85769 times cos of 56.3. So fx comes out to be, you can do the calculation, 34.857, take the whole value when you do the subparts, so it will be 19.34 Newton, right? Yeah. Now we got the fx, we know the fy, so f will be under root of, we know this resultant is fx square plus fy square, right? Now if you solve for this, putting up the values of the fx and fy and taking this under root, you will get the force something around, I have done the calculation, it will be 34.85. wait, fy is 29, fx is 19.34. yeah, so something around, you will get the force as 34.854, which is equals to 35 Newton. So this will be the answer for the magnitude, and for direction we can say tan theta will be equals to fy by fx, so 29 over 30, 19.34. so theta comes out to be something around, you can do the calculation, it will come 56.31 degree. So this will be the angle with horizontal. So this is how you solve the question number 1. I hope it is quite clear. If you have any doubt, just let me know, you can comment below. Okay, now pause the video, keep going and solve question number 2. Okay, so if I want to find out the minimum coefficient of static friction, let us first draw the forces in the given situation, right? So a uniform ladder is there, so a weight will be acting vertically downward in this direction, and it is in contact with the walls at 2 points, so there will be normal reaction, one will, and normal is always perpendicular, we discussed in our previous video, and let us consider this in another normal as r. Now this is supposed to slide like this, so the friction will be acting in this direction. There is no friction on the wall, but the floor has a friction, so friction will be acting in this direction. So these are the forces acting. Okay, now what we can do is, again we have to calculate the minimum coefficient of static friction between the ladder and the floor, so that the ladder does not slip. The angle is 60 degree. Now if you look at the horizontal forces, what I can make a comment about this is that your forces in the horizontal and the forces in the vertical are balanced. So for translational equilibrium, what I can comment is the normal reaction force will be equals to the friction, this normal reaction force will be equals to the friction, and this normal reaction force will be equals to the weight. So W will be equals to R. Now again for rotational equilibrium, what I can say, like if I considered any point, you can consider it as a pivot, such that the forces on that particular, you have the minimum forces to take into. So if I take this point, so I don't have to take the torque for these two forces, because the distance from them will be 0 and the torque will be 0. So I take this point as my pivot. So I'm taking this point as my pivot about which the ladder may rotate. So the two forces which are having a torque due to this point will be the normal reaction force, this one, and the weight. Now this will be the normal force of action and this will be the perpendicular distance, right? So if we have this as 5, so this will be 5 sine 60, right? So this distance, let us mark this distance. This distance will be 5 sine of 60, right? And similarly, the force of action for W is this. So this will be the perpendicular distance. So, and this is the midpoint where we have considered the weight of the rod. So this will be 2.5 and this is 60. So this distance will be 2.5 cos 60. So this is the line of action. This is the pivot point. So this distance we can consider this distance as 2.5 cos 60. Now for if you look at the forces, this will act as a clockwise movement and this will act as a anti-clockwise movement. So assuming, or we can say not assuming, we can say if this is in rotational equilibrium, the torque in the anti-clockwise direction will be equals to the torque in clockwise direction. So anti-clockwise will be the normal reaction force time F5 sine of 60. Similarly, clockwise will be the weight times 2.5 cos 60, right? Now if you look, we have the weight of the ladder is 350 Newton as given in the question. So the normal reaction force is 350 times 2.5 into cos 60 upon 5 times sine 60. Now when you put up the values in your calculator for normal reaction force, the N comes out to be something near to 101 Newton, right? Now this 101 Newton is equals to the friction, and friction, so friction is equals to nu times R, and the coefficient of static friction we have to find out, and R is equals to W. So we can say R is equals to 350 because R is equals to W, right? So we can write nu as friction over R, and friction is equals to N, and friction is equals to N equals to 101 Newton, right? So this will be nu is equals to 101 divided by R, which is 350. So if you put up the values, you will get nearly nu as 0.29 into two significant figures. Okay, so this will be your answer for question number 2. I hope it is quite clear. Just go through it once again. Even though if you find any doubt, just let me know. Now think about it and solve the question number 3. For this you will need the moment of inertia of a sphere, which is mr square, and for rod it is half ml square. Okay, so this you can try now. Pause the video and solve question number 3. Okay, now the A part is nothing but we have to find out the overall moment of inertia of the given arrangement. Okay, so if this is the axis of rotation, what I can say is there are two identical spheres. So I can say 2 times of, so total moment of inertia will be 2 times of m into r square plus 1 by 2 times of m into length. So this length will be, this will be the length for the rod L, okay, and this will be ml square. So if you just put up the values, it will be 2 into mass of the balls are 2 into radius will be 0.35 square plus 1 by 2 mass of the rod m2 will be 0.4 grams So 0.4 into length will be 0.35 square, because this is the axis of rotation. Okay, so we will take the length of the, sorry, length is not 0, length is 0.56, so it will be 0.56 square. So this will be the length, this will be the length, 0.56 centimeter. Okay, now put up the values in your calculator and solve. I have already done the calculation. When you solve this, this will come out 0.49 plus this will be something 0.010453. So if you add this, it will be 0.50045. As you can see, or rounding off, it will be 0.5 kg per meter square. Sorry, kg meter square. So this will be the answer for your part A. I have already done the calculation. You can check in your display calculator. Now the B part is calculate the percentage that the rod contributes to the overall moment of inertia of the system. Now we know that the individual is 0.010453 up, and the total is 0.50045 times 100. So this will be the contribution, and if you solve this, it will something near around 2.1%. So this will be the answer for B part. Okay, this is quite easy, guys. So this is how we find out the total moment of inertia. This will be given in the question itself. No need to remember like. If there is a different orientation about the axis of rotation, they will give you the moment of inertia for each individual object. You just have to use the principle of moment, which will be the addition of the moment of inertia about the given axis of rotation for each object. Okay, now well done till now. You have solved many questions. Now pause the video and solve question number 4. Okay, now if you look for the A part, the net force acting on the disk. Now there are only two forces and both the forces are in the same direction. So I can simply say that the net force is nothing but F1 plus F2, which is 3 plus 4, which is 7 Newton. So that's the answer, very simple. So this was the first part. Now the second part is the net torque about the center P of the disk. Now we know that the torque is the force times perpendicular distance. So the force is in this direction and this point is this. So what I can do is I take the component of the force which is perpendicular to the distance. So this is 90 degrees. So if this is F1, this is 40. So the perpendicular component of F1, this will be tangential to the, this will be tangential. So this will be F1 sine 40 and the distance will be 0.5 only, and this is already in perpendicular with the center of rotation. So this will be F2 times 0.2. But again, if I want to find out the net torque, so net torque will be considering the direction. So this will act for, this will be your clockwise and F2 will act for anti-clockwise. So the net torque will be just assuming clockwise as positive, so clockwise torque minus anti-clockwise torque. So clockwise torque will be F1 sine 40 times 0.5 minus anti-clockwise will be F2, which is 4 times 0.2. Now put up the values, and this will be F2. F1 is 3 sine 40 0.5. So this will be 3 sine 40 times 0.5 minus 4 into 0.2. So I have already done the calculation. You will get the answer something near to where is the answer? I have 0.5 0.16 Newton meter, and that too in clockwise direction. So you have to mention the directions also, otherwise you will lose your marks. Now the moment of inertia of the disk is this. Calculate the initial angular acceleration of the disk. Now let me make some space. Okay. Now for the B part, what I can say is, if the moment of inertia is this, we know that torque is equals to I alpha, right? So alpha will be torque upon I, that will be the net torque. So net torque is 0.16 upon I is 0.08. So if you look at this, this is nothing but 2 radian per second square. So this will be your answer for the B part. Okay, I hope it is quite clear. Now the last question of the video, actually you can do question number 5. Just pause the video and solve. Okay, now if you look at the A part, we have to find out the frictional torque acting on the wheel. Now for the frictional torque, if you look at the information, we have the moment of inertia, it rotates at an angular velocity is given. When applies brake, 1/4 of the revolution before coming off to the rest. So if I use omega final square equals to omega initial square plus 2 alpha into theta. Now 1/4 of revolution is theta is equals to pi by 2, because one full revolution is 2 pi, half will be pi, 1/4 will be pi by 2, right? So finally it is becoming 0. This is 23 square. This will be minus because it is deaccelerating. It is the application of brake times pi by 2. So this 2 and this 2 gets cancelled. So your alpha comes out to be 23 square divided by pi. So I have already done the calculation. Alpha comes out to be something near to 168.3859 radian per second square, right? Now this is the alpha. Okay, and torque is equals to, because this is the torque due to the frictional force, so torque will be I times alpha. Now the frictional torque, this is the frictional torque, will be I is given in the equation 0.09 times 168.3859. So if you do this calculation, you will get something around 15 Newton meter. So this will be the answer for your frictional torque. Okay, I hope it is quite clear. Now the wheel is equipped with a disc brake in which a force is applied to a disc by a pair of braking pads, one on each side of the disc at a distance of 8 cm from the axis of rotation of the wheel. The coefficient of the dynamic friction is given to us is 0.85. We have to calculate the magnitude of the normal force acting between the disc and each braking pad. Now if you look at the pad, the braking will be applied on both the sides. So this torque which we have calculated will be distributed over the two parts. So what I can do is, the torque for this will be 15, at the exact value is 15.1 divided by 2. Now this torque will be responsible for the application of the brake. So the normal force, we can say the torque is equals to F into D, as it is applying perpendicularly. So I can say 15.1 divided by 2 is the friction force times distance, which is 0.08, which is 8 cm, right? So friction comes out to be something around 94.717 Newton. So this will be the friction force, and friction is equals to nu into N, that is the normal reaction force. So your normal reaction force will be 94.717 divided by 0.85, which is the coefficient of friction. So the normal force comes out to be nearly, in two significant figure, is 110 Newton. Okay, so I hope this is quite clear. So this is the way, guys, you have to use the given equations for the torque. There are two equations for the torque. One is I alpha and one is the F r sin theta. Now when you are using FR sin theta, the most easiest way is to consider the force which is perpendicular to the distance from the pivot. So the distance and the force should be perpendicular. So this force component, if you do it automatically, you will get the right answer. If you have any doubt, just comment below and please share this video. And if you want one-to-one session with me, the link is given in the description. So keep learning with me. See you in the next video. Take care. Bye-bye.